Hello, I'm Robert Miles. Welcome to this recording of the Alignment Newsletter podcast. This is newsletter number 163, Using Finite Factored Sets for Causal and Temporal Inference, published on the 8th of September 2021 by Rohin. This newsletter is a combined summary and opinion for the Finite Factored Sets sequence by Scott Garrabrant. I, meaning Rohin, have taken a lot more liberty than I usually do with the interpretation of the results. Scott may or may not agree with these interpretations. Section Motivation. One view on the importance of deep learning is that it allows you to automatically learn the features that are relevant for some task of interest. Instead of having to handcraft features using domain knowledge, we simply point a neural net at an appropriate dataset, and it figures out the right features. Arguably, this is the majority of what makes up intelligent cognition. In humans, it seems very analogous to System 1, which we use for most decisions and actions. We're also able to infer causal relations between the resulting features. Unfortunately, existing models of causal inference don't model these learned features. They instead assume that the features are already given to you. Finite Factored Sets, FFS, provide a theory which can talk directly about different possible ways to featureize the space of outcomes and still allows you to perform causal inference. This sequence develops this underlying theory and demonstrates a few examples of using finite factored sets to perform causal inference given only observational data. Another application is to embedded agency, see newsletter 31. We would like to think of agency as a way to featureize the world into an agent feature and an environment feature that together interact to determine the world. In Cartesian frames, see newsletter 127, we worked with a function from A times E to W, where pairs of agent and environment together determine the world. In the finite factored set regime, we think of A and E as features, and the space S equals A times E as the set of possible feature vectors, and S to W as the mapping from feature vectors to actual world states. Section What is a finite factored set? Generalizing this idea to apply more broadly, we will assume that there's a set of possible worlds, omega, a set S of arbitrary elements, which we will eventually interpret as feature vectors, and a function f from S to omega that maps feature vectors to world states. Our goal is to have some notion of features of elements of S. Normally, when working with sets, we identify a feature value with the set of elements that have that value. For example, we can identify red as the set of all red objects, and in some versions of mathematics, we define 2 to be the set of all sets that have exactly 2 elements. So we define a feature to be a partition of S into subsets, where each subset corresponds to one of the possible feature values. We can also interpret a feature as a question about items in S, and the values as possible answers to that question. I'll be using that terminology going forward. A finite factored set is then given by S, B, where B is a set of factors, questions, such that if you choose a particular answer to every question, that uniquely determines an element in S, and vice versa. We'll put aside the set of possible worlds, omega. For now, we're just going to focus on the theory of these SB pairs. Let's look at a contrived example. Consider S equals a set containing chai, Caesar salad, lasagna, lava cake, Sprite, and strawberry sorbet. Here are some possible questions for this S. Food type. Possible answers are drink equals a set containing chai and Sprite, dessert equals a set containing lava cake and strawberry sorbet, and savory equals a set containing Caesar salad and lasagna. Temperature, where possible answers are hot equals a set containing chai, lava cake and lasagna, and cold equals a set containing Sprite, strawberry sorbet, and Caesar salad. Starting letter. Possible answers are C equals chai and Caesar salad, L equals lasagna and lava cake, and S equals Sprite and strawberry sorbet. And number of words, where possible answers are 1 equals chai, lasagna, and Sprite, and 2 equals Caesar salad, lava cake, and strawberry sorbet. Given these questions, we could factor S into the set of food type and temperature, or the set of starting letter and number of words. We cannot factor it into, say, the set of starting letter and temperature because if we get starting letter equals L and temperature equals hot, that does not uniquely determine an element in S. It could be either lava cake or lasagna. Which of the two factorizations should we use? We're not going to delve too deeply into this question, but you could imagine that if you were interested in questions like, does this need to be put in a glass, you might be more interested in the food type and temperature factorization. Just to appreciate the castle of abstractions we've built, here's the finite factored set F with the factorization food type and temperature. There follows a thing which is just very difficult to read out in a way that will be clear because it goes down to sort of 4 layers of indentation. I'm going to read it out literally with the punctuation to give you a feel for it, but I don't know if this is going to be followable. So, the finite factored set F with the factorization of food type and temperature. F equals, open bracket, open brace, chai, Caesar salad, lasagna, lava cake, Sprite, strawberry sorbet, close brace, comma, 3 open braces, chai, comma, Sprite, close brace, comma, open brace, lava cake, strawberry sorbet, close brace, comma, open brace, Caesar salad, lasagna, close brace, comma, open brace, chai, lava cake, lasagna, close brace, comma, open brace, Sprite, strawberry sorbet, Caesar salad, 3 close braces, close bracket. To keep it all straight, just remember, a factorization B is a set of questions, that is, factors or partitions, each of which is a set of possible answers, that is, parts, each of which is a set of elements in S. A brief interlude. Some objections you might have about stuff we've talked about so far. Question: why do we bother with the set S? Couldn't we just have the set of questions B and then talk about answer vectors of the form A1, A2, ... AN? Answer: you could in theory do this, as there's a bijection between S and the Cartesian product of the sets in B. However, the problem with this framing is that it's hard to talk about other derived features. For example, the question, what is the value of B1 plus B2, has no easy description in this framing. When we instead directly work with S, the B1 plus B2 question is just another partition of S, just like B1 or B2 individually. Question: why does F map S to omega? Doesn't this mean that a feature vector uniquely determines a world state, whereas it's usually the opposite in machine learning? Answer: this is true, but here the idea is that the set of features together captures all the information within the setting we're considering. You could think of feature vectors in deep learning as only capturing an important subset of all of the features, which we'd have to do in practice since we only have bounded computation, and those features are not enough to determine world states. Section Orthogonality in Finite Factored Sets. We're eventually going to use finite factored sets similarly to Pearlian causal models to infer which questions, random variables, are conditionally independent of each other. However, our analysis will apply to arbitrary questions, unlike Pearlian models, which can only talk about independence between the predefined variables from which the causal model is built. Just like Pearl, we will talk about conditioning on evidence. Given evidence E, a subset of S, we can observe that we are within E. In the formal setup, this looks like erasing all elements that are not in E from all questions, answers, factors, etc. Unlike Pearl, we're going to assume that all of our factors are independent from each other. In Pearlian causal models, the random variables are typically not independent from each other. For example, you might have a model with 2 binary variables. For example, variable rain causes variable wet sidewalk. Well, these are obviously not independent. An analogous finite factored set would have 3 factors. Did it rain? If it rained, did the sidewalk get wet? And if it didn't rain, did the sidewalk get wet? This way, all 3 factors can be independent of each other. We'll still be able to ask whether wet sidewalk is independent of rain, since wet sidewalk is just another question about the set S. It just isn't one of the underlying factors anymore. The point of this independence is to allow us to reason about counterfactuals. It should be possible to say, imagine the element S, except with underlying factor B2 changed to have value V. As a result, our definitions will include clauses that say, and make sure we can still take counterfactuals. For example, let's talk about the history of a question X, which for now you can think of as the factors relevant to X. The history of X given E is the smallest set of factors such that 1. If you know the answers to these factors, then you can infer the answer to x, and 2. Any factors that are not in the history are independent of x. As suggested above, we can think of this as being about counterfactuals. We're saying that for any such factor, we can counterfactually change its answer, and this will remain consistent with the evidence E. A technicality on the second point: we'll never be able to counterfactually change a factor to a value that is never found in the evidence. This is fine and doesn't prevent things from being independent. Time for an example. Consider the set S equals 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1, and the factorization x, y, z, where x is the question, what is the first bit, y is the question, what is the second bit, and z is the question, what is the third bit. Consider the question q equals, when interpreted as a binary number, is the number greater than or equal to 2? In this case, the history of q given no evidence is the set of x and y, because you can determine the answer to q with the combination of x and y. You can still counterfact on anything, since there's no evidence to be inconsistent with. Let's consider an example with evidence. Suppose we observe that all the bits are equal, that is, E equals the set of 0, 0, 0 and 1, 1, 1. Now, what is the history of x? If there weren't any evidence, the history would just be the set containing x. You only need to know x in order to determine the value of x. However, suppose we learned that x equals 0, implying that our element is 0, 0, 0. We can't counterfact on y or z, since that would produce 0, 1, 0 or 0, 0, 1, both of which are inconsistent with the evidence. So given this evidence, the history of x is actually the set of x, y, and z, i.e. the entire set of factors. If we'd only observed that the first two bits were equal, so E equals the set of 0, 0, 0, 0, 0, 1, 1, 1, 0, and 1, 1, 1, then we could counterfact on z, and the history of x would be the set of x and y. Should you want more examples, you can read the post, A Simple Example of Conditional Orthogonality in Finite Factored Sets, or A Second Example of Conditional Orthogonality in Finite Factored Sets, both by Daniel Phelan on the AI Alignment Forum. Given this notion of history, it's easy to define orthogonality. X is orthogonal to y given evidence E if the history of x given evidence E has no overlap with the history of y given evidence E. Intuitively, this means that the factors relevant to x are completely separate from those relevant to y, so there cannot be any entanglement between x and y. For a question z, we say that x is orthogonal to y given z if we have that x is orthogonal to y given little z for every possible answer little z in z. Now that we've defined orthogonality, we can state the fundamental theorem of finite factored sets. Given some questions, x, y, and z, about a finite factored set F, x is orthogonal to y given z if and only if, in every probability distribution on F, x is conditionally independent of y given z. That is, the probability of x, y given z is equal to the probability of x given z times the probability of y given z. Now, I haven't told you how you put a probability distribution on F. It's exactly what you would think. You assign a probability to every possible answer in every factor, and then the probability of an individual element is defined to be the product of the probabilities of its answers across all the factors. I also haven't given you any intuition about why this theorem holds. Unfortunately, I don't have great intuition for this. The proof has multiple non-trivial steps, each of which I locally understand and have intuition for, but globally it's just a sequence of non-trivial steps to me. Here's an attempt which isn't very good. We specifically defined orthogonality to capture all the relevant information for a question, in particular by having that second condition, requiring that we be able to counterfact on other factors, and so it intuitively makes sense that if the relevant information doesn't overlap, then there can't be a way for the probability distribution to have interactions between the variables. The fundamental theorem is in some sense a justification for calling the property orthogonality. If we determine just by studying the structure of the finite factored set that x is orthogonal to y given z, then we know that this implies conditional independence in the true probability distribution, whatever it ends up being. Pearlian models have a similar theorem, where the graphical property of D-separation implies conditional independence. Section Foundations of Causality and Time. You might be wondering why we've been calling the minimal set of relevant factors history. The core philosophical idea is that if you have the right factorization, then time, or causality, can be thought of as flowing in the direction of larger histories. Specifically, we say that x is before y if the history of x is a subset of the history of y. We then call it history because every factor in the history of x will be before x by this definition. One intuition pump for this is that in physics, if an event A causes an event B, then the past light cone of A is a subset of the past light cone of B, and A happens before B in every possible reference frame. But perhaps the best argument for thinking of this as causality is that we can actually use this notion of time or causality to perform causal inference. Before I talk about that, let's see what this looks like in Pearlian models. Strictly speaking, in Pearlian models, the edges do not have to correspond to causality. Formally, they only represent conditional independence assumptions on a probability distribution. However, consider the following cool fact. For some Pearlian models, if you have observational data that is generated from that model, you can recover the exact graphical structure of the generating model just by looking at the observational data. In this case, you really are inferring cause and effect relationships from observational data. In the general case where the data is generated by an arbitrary model, you can recover a lot of the structure of the model but be uncertain about the direction of some of the edges, so you're still doing some causal inference from observational data. We will do something similar. We'll use our notion of before to perform causal inference given observational data. Section Temporal Inference, the three dependent bits. You are given statistical, i.e. observational data for 3 bits, x, y, and z. You quickly notice that it's always the case that z equals x exclusive or y, which implies that x equals y XOR z and y equals z XOR x. Clearly, there are only 2 independent bits here, and the other bit is derived as the XOR of the 2 independent bits. From the raw statistical data, can you tell which bits are the independent ones and which one is the derived one, thus inferring which one was caused by the other 2? It turns out you can. Specifically, you want to look for which 2 bits are orthogonal to each other. That is, you want to check whether we approximately have probability of x, y equals probability of x times probability of y, and similarly for other possible pairings. In the world where 2 of the bits were generated by a biased coin, you will find exactly one pair that is orthogonal in this way. The case where the bits are generated by a fair coin is a special case. The argument won't work there, but it's in some sense accidental, and happens because the probability of 0.5 is very special. Let's suppose that the orthogonal pair was x and z. In that case, we can prove that in every finite factored set that models this situation, x and z come before y, i.e. their histories are strict subsets of y's history. Thus, we've inferred causality using only observational data. And unlike with Pearlian models, we did this in a case where one variable was a deterministic function of 2 other variables, which is a type of situation that Pearlian models struggle to handle. Section Future Work. Remember that motivation section a couple thousand words ago? We talked about how we can do causal inference with learned featureizations and apply it to embedded agency. Well, we actually haven't done that yet, beyond a few examples of causal inference, as in the example above. There's a lot of future work to be done in applying it to the case that motivated it in the first place. The author wrote up potential future work in the post Finite Factored Sets : Applications, which has categories for both causal inference and embedded agency, and also adds a third one, generalizing the theory to infinite sets. If you're interested in this framework, there are many avenues for pushing it forward. This concludes Alignment Newsletter number 163. For more information, you can go to rohinshah.com/alignment-newsletter, where you can find all of the previous newsletters and also a spreadsheet of all of the papers and summaries that have ever been featured. Thank you for listening.